Application of the flip-flops, or application of the counters. There are many applications. You can do a timing Unix. You can see traffic light. There are a lot of timing. You can count, and then after count to certain time, or in short, we call mode 16 counter. And you can call divide by 16 counter. So take note, people always confuse modular 2, modular 16, or because this view that the modular equal the number of state. Or here also, I explained to you before, the counter with m state is called modular m counter. Okay, please remember this because a lot of students confuse with the number of state variable or number of flip-flop and the modular. Okay, let me continue. And now you look at timing like that, you can understand what I'm trying to say just now. Okay, now for clock age, starting with just now the 6 sequence, Q0 is keep toggling. When Q0 equal to 1, Q1 will toggle. 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 Q0 equal to 1, Q0 will toggle. If Q0 equal to 0, the Q1 will remain. And you can see a gray color one. When Q0 is equal to 1, Q1 will toggle. Q0 equal to 1, Q1 will toggle. Let's look at the Q1 and Q2 relationship. When Q1 equal to 1, Q1 equal to 1, which is this state. Correct? And then Q0 and Q1 equal to 1, both of them equal to 1, Q2 will toggle. When both of them equal to 1, Q2 will toggle. Both of them equal to 1, Q2 will toggle. Both of them equal to 1, Q2 will toggle. Whereas for Q3, it will happen only when both 3 of them equal to 1, then it will toggle. When 3 of them equal to 1, it will toggle. So this gives us a counting from 0, 0, 0, 0, 0, 0, 0, or 0, 0, sorry, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and so on to count up. When it now reach the 1, 1, 1, 1, it will go back to all toggle together because this one always toggle. This one toggle when the Q not is equal to 0, is equal to 1. And this is toggle when both Q1 and Q not equal to 1. And this happens when both 3 of them equal to 1. So all will toggle together, all go back to 0, 0, 0, 0. And if you look at it carefully, if I change it to positive clock age, you will realize that it actually turned out to be the positive countdown counter, which later I'll show more example. So let us learn about how to design a count up counter first. So just now I mentioned to you the count up counter, we are tying them into the toggling mode. Okay, we are using J and K all tied together. If you have a D flip-flop, you cannot use as counter. So you cannot use SR because SR don't have toggling mode. So the counter only can use 2 types of flip-flops. One is JK, one is T flip-flops. And JK, we always tie the 2 J and K together as one to use as toggle mode. Okay, and then if J and K equals 0, it means that rest. So now, if you look at here, I'm adding the controlling circuit. Why I want to add controlling circuit? I haven't added yet because controlling circuit will allow me to reset, not count up to maximum. For example, I have this overflow here. I can use this one to cascade to another counting sequence, and these are called control circuitry. So used to drive cascading counter module, which also called Ripple carry out. Ripple carry out can count to, for example, now you have 4 bits, I can cascade to another 4 bits, so become 8 bits counter. And also I can use the sum of the circuitry to count until 10, then I will create. So you always count till 9, you will stop, or you go back to 0. Because why? Count to 10 the time, you will start to clear the whole circuit, go back to 0, 0, 0, 0. So these are called control circuitry. And then these are pure flip-flops to create a counter. So the counter can be very simple, which is a flip-flop, but you need to have control circuitry to go according to the sequence that you want. And here there is we call it the clock gator. Clock gator means that it gate the clock. Clock gator. G is like a gate. G-A-T-E. It gate the clock. It's like a gate here. Imagine, you know that the clock signal coming in order to create a count or counting sequence. But if I set it to 0, means that here always be 1, even though the counting sequence coming in is the clock signal. But you know that this is a 0 dominant gate. When 0 dominant gate means that when it's 0, output always go to 1. When output go to 1, it is not counting. If it's not counting, the output will be all hold at the stick. For example, you count until 15, it will stop at 15. The output will not be counting anymore. So you use this particular NAND gate, use it as a clock gator to gate the clock. So the clock cannot come in. If the clock cannot come in, it cannot continue the counting. So just now we learned about synchronous counter. Now we want to learn about asynchronous counter. In here, asynchronous counter also give a name called Ripple counter. So people tell you that, can you design a Ripple counter? You will know that you use asynchronous counter. And for the asynchronous counter, it means that the clock input of some or all the flip-flops are triggering by transition in other flip-flops output instead of a common clock signal. This means that in earlier part, what we learned is that every flip-flop tied to the same clock signal. Now, some of flip-flop, it tied to the previous Q output. And then continue to tie to previous Q output. So the first Q output go to the clock of the second Q of the second flip-flop. Then the second Q of the second flip-flop go to the input of the clock signal of the third flip-flop, and so on. So that's a mean called Ripple. So that's why the asynchronous circuit is actually, you need to have a lesser circuitry. Each flip-flop within the counter do not change state simultaneously due to the propagation delay. Because you can see that first flip-flop has some propagation delay, second flip-flop there also has some propagation delay, third flip-flop also has some propagation delay, so you can see the delay is rippled down. It means that delay will get longer and longer. So they will not output together at the same time because there is no common clock signal. By eliminating the requirement of the clock synchronization, a reduced amount of circuitry can be used to implement a binary counter. What it means is that this asynchronous counter is easier to design with a lesser circuitry, because in a synchronous counter, you need to clock together, therefore you need to have some control circuitry. In the asynchronous circuit, later I'm going to show you, it is a reduced amount of circuitry in here. However, the asynchronous counter suffers from the change of flip-flop propagation delay, because you have to continue to so-called accumulate the propagation delay. That's why you realize that the output might not go out simultaneously and might not be so good if you have a long change of flip-flops. So here, this signal show you that like you touch the water, you see the propagation, it comes to the other side, it will take longer time to reach the outer ring. So this is the meaning of ripple. So in here, let us look at the we call three state variable, or n equal to three flip-flops. Now you have 0, 0, 0, 0, 0, 1, 0, 1, 0 until 1, 1, 1, then go back to 0, 0 again. So this is a 3-bit asynchronous binary up counter. So similarly, the T0 is toggle every time. What about T1? It toggle when T0 equal to 1. So this means that when you design, you can use a simple standard design, tie the first flip-flop, go through the, we call high, and then after JK go to high, and then the clock signal can go to here. Just now I use a negative H trigger, I generate an up counter. Now I use positive H trigger, I will generate a down counter, correct? But if I still want to generate up counter, then I don't take from Q, I take from Q bar. Okay? This means that when you want to design up or down counter, you can use two ways. One way use we call it the positive or negative H trigger. One way is to use a Q0 or Q0 bar. So now, if I want to design a positive H trigger, I can use a negative H trigger and take the Q0 as the output. I want to have a positive H trigger by using I want to have a count up counter using the positive H trigger, then I have to take from Q0 bar. So now, because of the signal triggering, it has to be 1 in order to trigger Q1. So I take from the clock, take from Q0 bar. Okay? And in this case, you realize that you do not have a common, we call it common this clock signal. Because just now earlier we mentioned that when the Q0 and Q1 change together, then you affect the Q2. Now you realize it propagates the signal. For example, in here, when Q0 is 1, change to 0, then it will toggle this Q1. 1 change to 0, it toggle the Q1. Correct? So it means that when Q0 bar, you act as this so-called as a clock signal now. So I'm not looking at a state where Q1, so-called Q0 is a state 1 tied to JK. I'm not using the method. I'm using the Q0 bar as a clock signal. So Q0 bar changing from the negative positive clock H. Q0 bar change from positive clock H. Okay, change from positive clock H means that Q0 is changed from negative clock H, because Q0 is opposite with Q0 bar. So now here we look at negative clock H. Okay, here Q0 bar is look at the positive clock H, but Q0 is look at negative clock H. So negative clock H, it changed the toggle of a Q1. Negative clock H, change the toggle of Q1. Negative H, negative falling H, I will change this falling H, I will change to toggle the Q1. Falling H, I will toggle Q1. You understand what I mean? Instead of using the Q tied to the JK as the state of 1 to toggle, I now use the changes of the state of the Q0 to toggle this Q1. So this method is good, because this method I don't need additional circuitry to measure about the so-called previous state and the current state, the status. So now you look at here this Q2 only depend on Q1 toggling. Your Q1 only toggling high to low is only when you high to low, then you will toggle the Q2. So this is a clock H. Now this is a clock H during here 1 to 0 is actually Q0 go to 0 to 1. So during the period here, you can realize that it will toggle only when the Q0 bar in this case change from 0 to 1, or during the rising H here. But because we are looking at the Q1 instead of Q1 bar, so I'm looking at the falling H. Is it clear, everybody? And then with this method, you realize that I do not need to have an AND gate. Just now, remember, I need to have a one AND gate at least for the 3-bit counters. 4-bit counter, I need to have 2 AND gates. Now I do not need to AND gates. But what is the disadvantage of using this method? Disadvantage of using this method, you realize that you will have a longer propagation delay. And now let's look at the first example. First example is that the timing diagram of a 3-bit asynchronous up counter, but it is ideal. Ideal means that there's a zero propagation delay. So zero propagation delay means that first Q0, it will change toggle every clock cycle. In here, positive clock edge. Okay, you go back to see again. You can see that 0 change to 1, 1 change to 0, 0 change to 1, 1 change to 0 at the positive clock edge. Okay, this is what I'm referring to, Q0. You will change. And when Q0 change at the negative clock edge, when Q0 change, it acts as a clock signal for the Q1. Instead of taking clock signal from the clock or from the CLK, I take a clock signal from the Q0. So Q0 changing, I will change at the falling edge. Because when I take Q0 bar, I use a positive clock edge. Now I take the Q0, I use a negative clock edge. So I change here, then I change here, and at the negative clock edge, I'll change the Q1 again. And then this positive clock edge, I don't change the Q1. Negative clock edge, I'll change the Q1 again. And you can go nicely. So you go from 0, 0, 0, 0, 0, 1, and all the way to 1, 1, 1, and you back to 0, 0 again. Because at the negative clock edge, output will change. Okay? And the first one is always toggle. First one is connect to the flip-flop. The JK connect to 1 as well as the clock signal to connect to the so-called the common clock signal. And the rest of clock signal is connected to from the Q0 and is connected from the Q1. And this is ideal case, means that there's no propagation delay. Let us look at what happens if there's a propagation delay. If there's a propagation delay, you realize that there's a problem. First problem is that clock to the Q0. Correct? And Q0 to the Q1. And what happened to this Q0 to Q1 and Q1 to Q2? So here the propagation delay is short because it's only one propagation delay from the clock signal, which is the TFF or TPFF. That's how we refer to, from clock to Q0. TPLH. Because why? Because here we call it the low to high signal, TPLH. The propagation delay for the output to go from low to high, which is a clock to the Q0. You learned about TPLH and TPHL before, right? Yeah, so this is TPLH. What about second one? Second one, when clock change at the positive clock edge, output go to low, and this is TPHL. And this TPHL and TPLH may not be same so-called the timing. So you have to calculate them based on the method we learned before. And what happened to here? Q1. Why Q1 come out so late? Your Q1 is depend on Q0 to Q1 delay. So now you have Q0 bar to Q1 delay. So this is a delay TPLH. So now your Q1 respect to original clock is longer delay now, 2 delay. And you can see that if you do a counter, you want to count them together. For example, I count 0, 0, 0, 0, 0, 1, and then 0, 1, 0. Now it becomes this time I cannot use it as a counting. I have to count start from here. 0, 1, 0 is start from here rather than start from here, which is not at the clock edge. And subsequently, come to the fourth clock cycle. Then you have a first propagation delay, which is TPHL from clock to Q. Second propagation delay, TPHL from the Q bar to Q1, Q0 bar to Q1. And also, you have a TPLH from Q1 bar to Q2. So you can see the Q2 will arrive after the ripple delay from the first part, second part, and third part. So the Q2 will have a very long delay. And this very long delay sometimes make the counting very difficult. Because this counting can be actually shorter time. This counting is a shorter time. And then from here, you can see this is a longer time. So when you have this problem, you realize that your counting sequence, the period might not be able to count it effectively. Although the transition is rapid. Transition is rapid means that transition is actually from here, it can be very short because we are looking at in terms of a nanosecond. But this nanosecond, it can generate unwanted transition condition if the counter outputs are used to drive combination logic circuit. Because imagine, here is going to drive this AND gate. One of the signal come out at the 1 propagation delay, one of the signal is come out at the 3 propagation delay. So the AND gate might receive a low to high, and this one low to high. And the AND gate output, it might be a low, and output after that still low theoretically, but it must go high temporarily and go down. We call raised circuit. Let me draw out the signal. It means that if you have for example, AND gate, if one of the signal is going low to high, the other signal is high to low, because of different in delay, because 0, 1 will go to output will be a 0, 1, 0 output will be a 0. While during a short period of time, it might be an output of 1 because of different delay. And here, because of different delay, output of 1 at this point, you will consider raised condition. Raised condition means that you generate a glitch because of a different delay. So next time you go to experiment in the lab, you realize that you see a lot of students, some of them have glitches. But this one is actually you have to take longer time. You have to analyze the delay, and then you carefully design it to ensure no glitches. So not so straightforward because you do not know which one will generate glitches, and you have to look at it carefully. It will take some time. But this is an issue that you have we call additional propagation delay that connected to the subsequent combination logic circuit. Okay, let us look at another design. This design is called asynchronous BCD decay counter. In here, the decay counter, it means that it's count to 10 only, or count to 9, sorry. Its decay is a decimal. So you have 10 state, modulo 10. But you will count from 000 to 1001, which is 9. And let us look at how to use asynchronous to design. To use asynchronous circuit to design, we call it Ripple counter. Just now we learned before. I use a positive clock edge, but I take from Q naught bar, remember? It will generate a positive count up counter. Now I use a negative clock edge. If I use a negative clock edge, then you will realize that I have to take from Q naught. If I take from Q naught bar, it will give me a countdown counter, which I want to explain to you later, but let's assume that I would want to cover countdown counter at this moment because too many things might get you confused. So just take note that if I use positive clock edge, I use negative clock edge, I take from Q naught will be a count up. Okay? So now with that, you can see that how am I going to design to this count to 9 and then reset? Because you know that if I don't do reset, it will continue to count until 1, 1, 1, 1. And 1, 1, 1, 1 is not BCD decay counter. 1, 1, 1, 1 will be binary up counter. So in here, when you count to 10, which is 1, 0, 1, 0, which is a Q3 equal to 1, Q1 equal to 1. So you take from the Q3 and Q1 both equal to 1, you will generate a 0. Because this clear signal, there's a bubble here. So it means there's a clear bar to so-called clear the flip-flops. So when you count to 10, then after you quickly reset. When quickly reset, it's not very quickly because actually there's some delay in this so-called NAND gate. So it will still show a little bit of glitch if this NAND gate delay is very long. But this is the best we can design using the asynchronous circuit. So in here, advantage of asynchronous circuit is simpler. I don't need to put AND gate here. And then here, this is a reset circuitry to ensure I count to 1001, and then after reset to 0000. Okay, let us look at the timing diagram for just now, the asynchronous BCD decay counter. Now you count to 0000, 0001, and so on until when you count to 1001, then you realize that you will continue to count. But when you continue to count during the period, short period, when you detected Q3 and Q1 equal to 1, very short period, the clear asynchronous clear input will be activated because it will go down. Once you go down, he will quickly reset the flip-flop or clear the flip-flop output to 0. So if you look at it carefully, you realize that there is a small glitch at this point, the so-called Q1. Q3, there's no glitch because it's going down. Anyway, it will go down. So it will not be affected so much from 1 to 0. But Q1 is actually go to high already, then I go back to low. So go high, go to low. In here we call glitch. Okay. So this glitch is not if you're not careful, design carefully, this glitch might make the output signal go to 0, 1, 0. Instead of supposed to receive a 0 throughout, now it becomes 0, 1, 0. So let us look at synchronous. Then how you design a synchronous BCD decay counter? When you talk about synchronous, remember, go back to the state we are talking about, designing the finite state machine. That's the powerfulness for synchronous. I can design any sequence because I based on state diagram. Asynchronous, you cannot base on state diagram. So synchronous, I based on state diagram. So current state is 0, 0, 0, 0. Next state, what is it? Next state is a 0, 0, 0, 1. Okay? And this 0, 0, 0, 1, what is the next state? Next state is 0, 0, 0, 0, 1, 0. But because I'm going to 0, 0, 1, 0 next state, I'm using the T flip-flop. T flip-flop, change from here to here is a toggle, change from here to here is a toggle. So T input is toggle, or T1 is 1, T0 is 1. This means that this is the T input. This is not the next state. The next state is here. From here to here is next state. 0, 0, 0, 0 is the current state. Next state is 0, 0, 0, 1. So from 0, 0, 0 to 0, 0, 0, 1, the T input should be 0, 0, 0, 1. 1 is toggle. So later you realize the advantage is that third one, you see that in order to generate from 0, 0, 0, 1 to 0, 0, 1, 0, so your T input should be 0, 0, 1, 1, because these two will create these two to toggle. Okay? Then here, from here 0, 0, 1, 0 to 0, 0, 1, 1. So only last bit need to be toggle. So that the input should be 0, 0, 0, 1. I continue. So in here, from this state 0, 0, 1, 1, you are going to change to state 0, 1, 0, 0, and 3 bits need to be toggle. So your input to the T flip-flop will be 0, 1, 1, 1. Okay, so this case means that it will be 0, 1, 1, 1. And subsequently, I'll just continue. From here, only this bit need to be toggle. And then from here, 2 bit need to be toggle. Next one, only last bit need to be toggle. This one, you realize that all the 4 bit need to be toggle. From 0, 1, 1, 1 to 1, 0, 0, 0, all the 4 bit are toggle. And then this will be the last bit need to be toggle. And this one, the 2 bit need to be toggle. And last one from here, 0 to go to 1. Again, 0, 0, 0 to go 0, 0, 1 is that the toggle input should be 0, 0, 0, 1. Any question before I go on to more explanation? Okay, now what is the next step? If it's T flip-flop, you can use a T0, T3, T2, T1, T0. If it's a JK flip-flop, you can tie them together, J and K tie together. So it's still the same. There's no difficulty saying that JK flip-flop is more difficult because you implement them like a T flip-flop. So when you say T0 equal to 1, it's equivalent to J0, K0 equal to 1. So now, let me just assume that I use a so-called, I work out the, remember we always say that we want to design the finite state machine, design finite state machine. First step is that state diagram. I hope you still can remember the only 5 steps. First step is state diagram. Second step is the state table. Third step is a K-map. Fourth step is the input to the flip-flops as well as circuit outputs. For the counter, there's no circuit outputs. And finally, it's a circuit. So you're following the finite state machine design to design the synchronous counter. You can imagine quite complicated. So that's why you realize that using synchronous counter, you can do any sequence, but the design as well as circuitry is more complicated. Just now I mentioned to you, you use asynchronous circuit design, you only need a 4 flip-flop. That's all. Here you need to have a, imagine you need to have, 4 flip-flop plus 1 NAND gate. Now you need to have so many circuits. Later, let me show you. So this is a state diagram. This is a K-map. After you generate K-map, you also generate these inputs to the flip-flops. Then after that, next step, what's the next step? What's the next step? After you have this Boolean equation, for the inputs to the flip-flops. Very good, it's a circuit tree. So you draw the circuit. And looking at this circuit, okay, let me continue. Q0 is a least significant bit. Oops, sorry. So this circuit tree, you have a good advantage. Advantage is that no propagation delay because the propagation delay maybe is 1 only. That means that from the clock to the flip-flop output. But however, you look at circuit tree, it has so many additional circuitry, plus also the design part is quite complicated. It's not just tied together. But advantage is the synchronous counter, it can design any sequence because the next stage is up to you to choose. You can jump from 0, 0, 0, 0 to 1, 1, 0, 0. So it's no sweat to do any sequence. Now let's look at the timing diagram. Timing diagram is very straightforward. I mean, we can know that because the next state is always depend on the design, previous state. So previous state, the current state is 0, 0, 0, 0. Next state will be 1, 0, 0, 0. And then this 0, 0, 1, 0, and then 0, 0, 1, 1. And for this design, you don't need to worry about negative clock edge, positive clock edge. Because you know finite state machine, you don't care about negative clock edge, positive clock edge, you move from one state to another state. Okay? And then in theory, you can design any flip-flop. You don't need to design using JK. In theory, you can design using D flip-flop. You can design using the toggle, except SR not allowed because you don't have toggle mode. So this means that you can use the method finite state machine to design any sequence, including the sequence now calling from the BCD counter, counting from 0, 0, 0, 0 to 1, 0, 0, 1, which is a 0 to 9 and reset to 0 again. Okay? So this means that when you talk about synchronous counter design, it is not so straightforward. But some of it, very simple one, binary counter. Yes, you can do that. But some of the difficult one, you have to use a complete FSM, finite state machine design method to do that. This is an example of the IC. This particular IC is called 74. 74 is referred to digital. 54 referred to digital military grade, which is higher temperature and faster speed. 160 is referred to the divided by 10 counter. In here, we can call it modular 10 counter. 4-bit, because you have 4 output. Synchronous, and this is a design for synchronous counter, BCD counter. So here you have input, D3, D2, D1, D0. Then you have clear signal to clear the output. You have load signal to load the input in. Once you load the input in, then here, when the load is equal to 0, data D will be synchronously loaded into the counter and will appear at output queue. For example, I load the 0, 0, 0, 0. I set this one to 0, output will become 0, 0, 0, 0. If I load the 0, 0, 0, 1, then if I load it, output will become 0, 0, 0, 1. Okay? After that, if you set the load equal to 1, then this one has no effect already. I'm not going to load it. Okay? No effect. After I load into the set this one to 1, I can start the counting. I can set the clock equal to high, low, high, low, high, low, high, low. Then after that, here output will be go from counting up or counting down. In this particular case, counting up. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. Okay, so this loading is only one time. Once you load it, then you can disable it and do the counting. And then here, you also have a enable parallel, enable trigger. Must be equal to 1 before counting is so-called these two pin. You have to set it to 1 before you can do the proper counting. So either one of them brought low to inhabit the counter. Means that assume I set EMP equal to 1, output will be stay at the, for example, I count until 1, 0, 0, 1, 0, 0, 0, it will stay. It's a temporary hold it. Then if I let go it will count from 0, 1, 0, 0, 0 and count to 1, 0, 0, 1 and continue. So these two are to temporary hold it. RCO is the high during the period of time where the counting is in state 9, maximum state. For example, you count to 9, you realize that this RCO will be equal to 1. The output equal to 1. Okay, so you count to 9. 9 is at Q3 and Q not equal to 1, and the ENT equal to 1. So this means that you stay there for until you reset it, until you clear the output and clear the, this so-called output as well as here. So this is a simple 4-bit synchronous counter. It's an IC. It's an IC. So this IC is a commonly used. So when you use IC, we need to know the internal circuitry. The internal circuitry of this IC is equal to this. So this is an internal circuitry for IC. Okay, so this 4 flip-flop we put together plus external part, the Q, 3 Q, 2 Q, 1 Q naught, as well as the D1, D2, JK, which is D in this case, you call it data. And then after that, this circuitry, we put into IC, it becomes 74160. Okay, any question? Okay, then this is the last part I want to show to you, timing diagram. Because when you look at IC, you cannot simply say that, oh, I know how to use it, but you need to look at timing diagram. First, you will load the data, or you clear the output first. You clear. So you clear the output asynchronously, means that you can hit push button, press it. Once you clear the output, Q will go to the, we call defined state. Because here it's undefined. Initially, we don't know what is output state. It could be undefined, could be 0, could be 1, could be in the middle. And then now once you clear it, it becomes 0, 0, 0, 0. And data, you do a load. Once you load already, the data input, which is D3, D2, D1, D0, in this case, called 0, 1, 1, 1, which is 7, you load onto the Q output. Okay, synchronous load. So output becomes 0, 1, 1, 1, which is same as the input. After you load already, you have to disable the load signal. Because you don't disable, you continue to load and load and load new data. Then now, after you disable the load already, also you have to disable this EMP and ENT. These two is just to want to do we call it the control. And now you are counting up. So let's assume it's counting up from here. You count from 7. The next count will be 8, 9, 0, 1, 2, 3. Okay, when you come to 3, then you realize that I activate the EMP. EMP is to, once you activate, you hold the line. During this period, when you count to 9, 1, 0, 0, 1, then you realize the RCO also hold to high. And when it's continue 9, you continue hold to high. But if it's the go to 0, then the so-called, if you go to the 9, after that you go to 0, 0, 0, 0, then this one RCO will go to low again. Then now when you activate the EMP, you realize the output will hold at the 3 continuously. Then if you deactivate the EMP but you activate ENT, output is still continue to be in habit, means that hold at 3. So this means that when you operate the IC or the circuit, you have to understand the function and the timing diagram. Because this is a sequential logic circuit, the output will not be the same if you have a different input and different state. Okay, this will be the last slide. Oh, not yet. Okay, this is the last slide. Okay, just now we talk about synchronous up counter. Count from 0 to 111 and go back to 0 again. Then there's a down counter. Count from 111 to 0, 0, 0 and go back to 111 again. Then you also can design using up-down control and with the clock signal. And then with this circuit, you can use the input. If input is 1, you will count up. If input is 0, you count down. So this means the Q output of the flip-flops control JK. Okay, control the JK terminals of the flip-flop higher interchange for up counter. Okay, so this design, in fact, is not difficult. You realize that for the finite state machine, you can design using a circle. For example, remember first state, you are in the, for example, this state is called 0, 0, 0, 0, 0, 0. If you are in the input is 1, you will go to where? Go to state 0, 0, 1. If input is go to 0, you will go to state. What is the state? 1, 1, 1. Okay, so you can continue to draw the state diagram. If you draw a state diagram, then after that state diagram, go to state table, go to the K-maps, go to the flip-flops inputs. There's no output in here. So then you can design the circuit. This is exactly the same method. It's not very difficult. There's only one input. The input is called up, down. Although the name looks very funny, but you can call it in. Okay, so this means that it is very simple to design a counter. Because counter has no output. This method can only use in the synchronous counter. Asynchronous counter, you cannot do the up-down counting. Okay, any question? Very simple, right? Okay, let's look at counter MCQ before we close so-called the topic. Good. So let us, sorry. how many flip-flops are required now? You have 4 bit, you can up to the 16. To count the Q3, Q2, Q1, Q0, and toggle every clock cycle. And what about Q1? Oh, so-called you can use the first flip-flop to generate a Q0 by tying the JK to high. If it's just a T flip-flop, you just tie the T to high. And clock signal, in here, you realize very interestingly, I use a negative clock edge for counting up. Later, I will explain to you. But now you can see that. Now, when you have a negative clock edge, I'll change from 0 to 1, 1 to 0, 0 to 1, 1 to 0. And the output here, Q0. Then Q1 is toggle when Q0 equal to 1. Q1 is only toggle when Q0 change from 1 to 0. Or when it is 1, then I will toggle. Because this is a current state. Toggle array, I go to next state. Current state 0, 1, next state 1, 0. So this means that Q1 will change when Q0 equal to 1. Q0 will change, and Q1 will change when Q means that you can design this way, because looking at the sequence, you can tell that. Then let's look at Q2. Q2 will only toggle when both Q1 and Q0 equal to 1. Both, Q0 and Q1 equal to negative change to 0. 1 change to 0, correct? 1 change to 0. Here it's very hard to count. Okay, never mind, I will show you a timing diagram, that's easier to explain. So can you tell me what is the modular for this particular counter? Modular what? No, we have 16 states. Number of state variable or number of flip-flop and the modular. Okay, let me continue. And now you look at timing diagram, you can understand what I'm trying to say just now. Okay, now for clock edge, starting with just now the sequence, Q0 is keep toggling. When Q0 equal to 1, Q1 will toggle. 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 Q0 equal to 1, Q0 will toggle. If Q0 equal to 0, the Q1 will remain. And you can see a gray color one. When Q0 is equal to 1, Q1 will toggle. Q0 equal to 1, Q1 will toggle. Then look at the Q1 and Q2 relationship. When Q1 equal to 1, Q1 equal to 1, which is this state. Correct? And then Q0 and Q1 equal to 1, both of them equal to 1, Q2 will toggle. When both of them equal to 1, Q2 will toggle. Both of them equal to 1, Q2 will toggle. Both of them equal to 1, only open 1. And this is toggle when both Q1 and Q2 to the toggle. Both 3 of them equal to 1. Count up counter first. So just now I mentioned, which later I'll show more example. Look at it carefully. If I change it to positive clock edge, you will realize that it actually turned out to be the positive countdown counter, which later I'll show more example. So let us learn about how to design a count up counter first. So just now I mentioned to you the count up counter, we are tying them into the toggling mode. Okay, we are using J and K all tied together. If you have a D flip-flop, you cannot use as counter. So you cannot use SR because SR don't have toggling mode. So the counter only can use 2 types of flip-flops. One is JK, one is T flip-flops. And JK, we always tie the 2 J and K together as one to use as toggle mode. Okay, and then if J and K equals 0, it means that rest. So now, if you look at here, I'm adding the controlling circuit. Why I want to add controlling circuit? I haven't added yet because controlling circuit will allow me to reset, not count up to maximum. For example, I have this overflow here. I can use this one to cascade to another counting sequence, and these are called control circuitry. So used to drive cascading counter module, which also called Ripple carry out. Ripple carry out can count to, for example, now you have 4 bits, I can cascade into another 4 bits, so become 8 bits counter. And also I can use the sum of the circuitry to count until 10, then I will create. So you always count till 9, you will stop, or you will go back to 0. Because why? Count to 10 the time, you will start to clear the whole circuit. Go back to 0, 0, 0, 0. So these are called control circuitry. And then these are pure flip-flops to create a counter. So the counter can be very simple, which is a flip-flops, but you need to have control circuitry to go according to a sequence that you want. And here there is we call it the clock gator. Clock gator means that it gate the clock. Clock gator, G-A-T. The clock is a gate here. Imagine, you know that the clock signal coming in in order to create a count or counting sequence. But if I set it to 0, means that here always be 1, even though the counting sequence coming in is the clock signal. But you know that this is the 0 dominant gate. When 0 dominant gate, it means that when it is 0, output always go to 1. When output go to 1, it is not counting. If it's not counting, the output will be all hold at the state. For example, you count until 15, it will stop at 15. The output will not be counting anymore. So you use this particular NAND gate, use it as a clock gator to gate the clock. So the clock cannot come in. If the clock cannot come in, it cannot continue the counting. So just now we learned about synchronous counter. Now we want to learn about asynchronous counter. In here, asynchronous counter also give a name called Ripper counter. So people tell you that, can you design a Ripper counter? You will know that you use asynchronous counter. And for the asynchronous counter, it means that the clock input of some or all the flip-flops are triggering by transition in other flip-flops output instead of a common clock signal. This means that in earlier part, what we learned is that every flip-flop tied to the same clock signal. Now, some of flip-flop, it tied to the previous Q output. And then continue to tie to previous Q output. So the first Q output go to the clock of the second Q of the second flip-flop. Then the second Q of the second flip-flop go to the input of the clock signal of the third flip-flop, and so on. So there's a name called Ripper. So that's why the asynchronous circuit is actually, you need to have a lesser circuitry. Each flip-flop within the counter do not change state simultaneously due to the propagation delay. Because you can see that first flip-flop has some propagation delay, second flip-flop also has some propagation delay, third flip-flop also has some propagation delay, so you can see a delay is rippled down. It means that delay will get longer and longer. So they will not output together at the same time because there is no common clock signal. By eliminating the requirement of the clock synchronization, a reduced amount of circuitry can be used to implement by counter together the initial delay. Because you have to continue to the propagation and it might not be so good if you have a long change of a flip-flop. Flip-flops. So here, this signal show you that like you touch the water, you see the propagation, it comes to the other side, it will take longer time to reach the outer ring. So this is the meaning of ripple. So in here, let us look at the we call three state variable, or n equal to three flip-flops. Now you have 0, 0, 0, 0, 0 again. What about T1? It toggle when it's a just now I use a positive, negative edge trigger. I generate an up counter. Now I use positive H trigger, I will generate a down counter, correct? But if I still want to generate up counter, then I don't take from Q, I take from Q bar. Okay? This means that when you want to design up or down counter, you can use two ways. One way use we call it the positive or negative H trigger. One way is to use a Q naught or Q naught bar. So now, if I want to design a positive H trigger, I can use a negative H trigger and take the Q naught as the output. I want to have a positive H trigger by using I want to have a count up counter using the positive H trigger, then I have to take from Q naught bar. So now, because of the signal triggering, it has to be 1 in order to trigger Q. Q1. So I take from the clock. So now, one way is to use the Q naught or Q, I take from Q bar. Okay? This means that when you want to design up or down counter, you can use two ways. One way use we call it the positive or negative H trigger. One way is to use a Q naught or Q naught bar. Now, if I want to design a positive H trigger, I can use a negative H trigger and take a Q naught as the output. I want to have a positive H trigger by using I want to have a count up counter using the positive H trigger, then I have to take from Q naught bar. So now
Discord. 请告诉我，今天爱是什么颜色？夜夜陪着你的海，心情又如何？灰色是不想说，蓝色是忧郁，而漂泊的你，狂浪的心停在哪里？写信告诉我，今夜你想要梦什么？梦里外的我，是否都让你无从选择？我就这一颗心，整夜都闭不了眼睛。为何你明明动了情，却又不靠近？听海哭的声音，叹息着谁又被伤了心，却还不清醒。一定不是我，至少我很冷静。可是泪水，就连泪水也都不相信。听海哭的声音，这片海未免也太多情，没提到甜蜜。写封信给我，就当最后约定，说你在离开我的时候是怎样的心情。你是我最痛苦的抉择，为何你从不放弃漂泊？爱对你是那么难分难舍，你总是带回满口袋的沙给我，难得来看我，却又离开我，让那手中泻落的沙像泪水流。风吹来的沙，落在嘴上的眼里，谁都看出我在等你。风吹来的沙，堆积在心里，是谁擦去的痕迹？风吹来的沙，穿过所有的记忆，谁都知道我在想你。风吹来的沙，明明在哭泣，难道早就预言了分离？你坠入我的心中，你在乎我的举动，哄得我泪眼迷蒙，做些事情让我被感动，望着你突然一阵心痛，一次又一次认了感情放纵， 你的脆弱让我走不开，你的依赖，所以我存在。想着你还是想到心痛，期待我做的将来你都会懂。有一天，只如果有一天，但愿我还在你记忆中。有一天，只如果有一天，但愿我还在你记忆中。邱林老师，谢谢你。我会努力就睡，爱在背后往前推，当我的指头才发觉，我是不是忘了谁？累到天也不能睡，夜深哪里都是美，一定有个人了，不过避过闪过迈过，一定不是我。至少我会冷静，可是泪水，就连泪水也都不相信。累到天也不能睡，夜深哪里都是美，一定有个人吧，躲过避过闪过，写封信给我，就到最后约定。说你在离开我的时候，是怎样的心情？他是谁？谢谢。如果有一天，同样的机场，不同世界，同样的咖啡，不同味觉，同样的我和我都少了一些。看飞机划过天空，不见了。圈圈圆圆圈圈，天天年年天天的我，深深看你脸，生气的肉，埋怨的肉的脸。不懂爱恨情仇煎熬的我们，都以为相爱就像风云的善变。相信那一天抵过永远，在这一刹那冻结的时间，只是简简单单的爱过我。 我还是我，简简单单的伤过，就不算白过，简简单单的风波被我带走。当故事结束之后，心也喜欢一个人寂寞。多么年分散过，烽火连天不休。儿女情长被乱世左右，谁带煮酒，尔虞我诈是三国，说不清对与错，纷纷扰扰千百年以后，一切又从头。大家好。只能眺望东边，你的世界太远哦，远到想象的极限。幸福有多甜，黑夜已吞噬我，就是拉不到你的手。借我你们的手，小酒窝长睫毛，迷人的舞歌就要我放慢了步调，感觉像是喝醉了。终于找到心有灵犀的美好，一辈子暖暖的好，我永远爱你到老。100天还是很有感觉，用眼睛去扫描你内心世界。第几个100天也像刚热恋，两个人手一牵，连命运都改变。曾有的敏感脆弱，在我的胸口，你就躺下来，别说了将有的苦的冲动，我也会拥抱你，安抚着，体谅你心疼着我。等不到天黑，烟火不会太完美，回忆烧成灰，还是等不到结尾。他曾说的无所谓，我怕一天一天被摧毁。等不到天黑，不敢表现的华美，绿叶在跟随，放开刺痛的滋味，今后不再怕天明，我想只是害怕清醒。会不会唱？让爱的故事声听说，找不到你单纯的面孔，当生命每分每秒都为你转动，心有多执着，就这会心痛。修炼爱情的悲欢， 我们这些努力不简单，快乐里的泪水是一种勇敢。几年前的幻想，几年后的原谅，回忆让人去养一人心想。别想想念我，我会受不了这样。楼上的朋友，笑着说爱让人疯狂，哭着说爱让人紧张，忘不了那个人就投降。那些你很冒险的梦，我陪你去疯。这只飞机碰到雨天，终究会坠落。太残忍的话我只说，因为爱很重，一切不想动，只往反方向走。尖叫声！到我那天，把该说的话好好说，该体谅的不执着。如果那天我不受情绪挑拨，你会怎么做？那么多如果，可能如果我，可惜没如果。梦未如理就睡，爱在背后往前推。当我抬起头，才发觉我是不是忘了谁？累到这夜不能睡，眼神哪里都是泪。一定有个人他过过飞过晒过爱过，他是谁？那之前我要到底在你留人潮，懂你每个泪和笑，从你故事中找到荣耀，努力不会徒劳，爱并非惆怅，我们握着手多好。You're crying in your bedroom, 'cause I'm gonna let you. Wish I never met you. Don't know what you got until it's gone. You're crying in your bedroom, easy to forget you. Turn this to yourself and now I'm gone, gone. 云风梦，爱过时光可以什么？记不住，忍不住，泪眼中谁一样脸红？等你说，等我说，一定就是一个宇宙。日升快乐落，只来换寂寞。骄傲日子也许忘了第几幕，那是我们身处第几号时空，以为我们手心紧握，记忆也能紧扣，可不怕前方的冲动。我拿孤独当娱乐，全然独特，跟不及人把风痴点着黑跟白银河，我拿着孤独娱乐，无奈没辙，到 前夫吧，其他不说了，痛比你快乐。痛心更快乐。也许忘了第几幕，那是我们身处第几号时空，以为我们手紧紧握记忆的尽头，可不把前方的冲动。我拿孤独当娱乐，全然独特，等我几年把风痴点上黑跟白银河，我拿着孤独娱乐，无奈背着痛。I've been waking up inside a wonderland I don't know. High above the clouds, now we're the ones who cast the shadows. Don't let me fall asleep, don't let me disbelieve. You gotta be the one to keep me focused. Get my heart open, I never felt this way. Swear you could change my name. You're gonna be the reason I'm unbroken. I'm gonna hold you all I can, 'cause you got me feeling things I don't understand. I'll give up my pride and all my plans. Every second you're with you is like falling sand. The more I hold, the more I lose, the more I know nothing lasts. The frames of glass, they break like bones. It don't matter if all this shatters, all this goes. I'll take the chance. I'm gonna hold you while I can. I can't take this. I keep slipping back. These old habits can't die too fast. Don't let me fall asleep. Don't let me disbelieve. You gotta be the one to keep me focused. Tear my heart open, I've never felt this way. Swear you could change my name. You're gonna be the reason I'm unbroken. I'm gonna hold you all I can. Cause you got me feeling things I don't understand. I'll give up my pride and all my plans. Every second you're with you is like falling sand. The more I hold, the more I lose, the more I know. Nothing lasts, the things of glass, they break like bones. It don't matter if all this shatters, all this goes. I'll take the chance. I'm gonna hold you all I can. I'm gonna hold you all I can. I'm gonna hold you all I can. Cause you got me feeling things I don't understand. I'll give up my pride and all my plans. Every second you're with you is like falling sand. I'm gonna hold you all I can. I'm gonna hold you all I can. I'm gonna hold you all I can.好像号角音符在空中飘荡，你也听见了吗？瞬间有了飘向未知的方向，你和我都一样，穿越人海和时间的浪，是谁的脸空刻在心上？带不走的就让它留下，转身前往下一个远方。每一个心都有着向往的地方，接着就会听见奇迹的声响。为了在那黑夜画出一道光，渴望信仰。几场落在风中摇起呀去闯，让我经历多少岁月的收藏，拥抱眼前看似渺小的希望，不让对方感受当下。写下一生途中不见的行囊，别再回头张望，望着这下一个藏什么宝藏，最终会有解答。这个人来了时间的浪，是谁的灵骨刻在心上？带不走的就让它留下，瞬间往心的航向。每一个心都有着向往的地方，现在就会听见奇迹的声响。未来在那黑夜画出一道光，渴望信仰。气场都在风吹摇起呀去闯，让我经历多少岁月的收藏，去拥抱眼前看似渺小的希望，不让对方感受当下。迎着狂风和孤单并肩流浪，就算前方看似无尽的迷惘，再渺小的希望，围着梦长大。每一个心都有着向往的地方，没有不会抓住梦让它去领航。当未来在那黑夜画出一道光，渴望信仰。 心降落在返归阳彼岸去闯，让我肩内多成岁月的收藏，用我眼睛看似渺小的希望，不让不放，那是力量。南辕北辙，挥着泛黄的皱褶是什么？交错的每一个转折，为什么？轻轻的、悄悄的哼着哼歌，他很快乐，说着带忧伤的眼笑都笑了。他还带完美的婚礼落幕了，我跟他虚构的故事结束了。不懂为无中梦，习惯了无处可躲，床头灯照亮眼前的寂寞。最好是我们都忘了，最好是我们不记得，嘘寒问暖中藏着生疏的温柔，听了我多不舍。最好是我们都忘了，最好是我们都不记得，钢琴键还跳动着黑白的余温，残留着你的指纹，又如何？期待什么？这首歌唱成了情感，所以呢，也跟他分享着同个心事了。看到照片里可爱的小孩要死了，没关系了，一时的如今能坦然说出口，曾经爱过的笑的深刻就够了，脑海里的画面少不了怎么也淡不掉颜色，一个人辗转反侧，这结局多欢乐，没你的空窗一点都不寂寞。最好是我们都忘了，最好是我们不记得，嘘寒问暖中藏着生疏的温柔，听了我多不舍。最好是我们都忘了，最好是我们都不记得，感情键还跳动着黑白的余温，残留着你的指纹，又如何？最好是昨天都忘了，最好是明天都不记得，平行时空重叠了，却没交集了，我还能做什么？也许是你真的忘了，也许是我记性太好了，该说的我说完了，听听就算了，晚上应该睡了，晚安了。 献给我们离开的那些。心里有种声音回荡在梦境，有些秘密不断的飘零，不断的在旅行，故事和冷静。谁还相信还在聆听所谓命运？北方到底还有几公里？想要离开又能去哪里？所有思绪都在等消息。原来离别难分类，谁亏欠谁？离开我们的那一些，原来放手也是一种美，一种的了解。不同的世界，不去追，离不开谁是谁，所谓爱很心碎，是因为你想拥有着故事的一切。风缓缓移动，梦闪烁如霓虹，谁在窗外弹琴，弹谁的曾经？所有风景，所有森林都在结冰。北方到底还有几公里？想要离开又能去哪里？所有思绪都在等消息。原来离别很难分类，谁亏欠谁？离开我们的那一些，原来放手也是一种美，一种的了解。不同的世界，不去追，离不开谁是谁，所谓爱很心碎，是因为你想拥有着故事的一切。离开我们的那一些，让割舍成为一种美，所谓的直觉。不同的风雪，不去写，向北风去面对自己，感受落叶，真话用成烟，落雨的伤被我拒绝。梦越过寒冬，爱放在我心中。 金鱼的毛往时间裂缝里看到了我，每天脚架之外的另一些我。乌云静止以后，跳进平行时空，那些我旅行中的你我，回忆胡乱穿梭坠落，交换一生是我非我，苦与乐，1年之后总有虚名的晴空。如果我们几经转折，结局一样不同，也才走回这分合。因为心爱的猫让时间停顿了，想慢动作。你说命运能外吧，幸好有我。如果没有以后，如果平行时空，那些我不同人生的我会以什么方式哭过？交换一生是我非我，苦与乐，明天之后总有虚名的晴空。如果我们几经转折，结局一样不同，也才走回这分合。云等风，人等梦，爱念过时光等什么？记不住，忍不住，泪眼中是一人脸红。等你说，等我说，一等就是一个宇宙。日升换月落，真爱换寂寞。叫我一生，也许忘了第几梦，那是我们身处第几号时空，因为我们手心紧握，记忆也能紧扣，可不怕肩膀的冲动，还是时间的鼓动。阳光并不普照，什么都看不到，看在手中的反而虚无缥缈。试问谁不孤傲，容不下结局太跳跃，却把余生铺成雷同的轨道。 每次当我沾染了黑暗的色调，想象自己有对照，在此刻在某处那个我，他很好。每次当我迷惑在眼前的美好，提醒自己更善良，这一生只是永恒暂时的记号。人的心很奇妙，越寂寞越喧嚣，抉择让你得到幸福，也带来烦恼。表象只是通道，熄火会最终同样单调。我们只是旅程其中的一条。每次当我沾染了黑暗的色调，想象自己有对照，在此刻在某处那个我，他很好。每次当我迷惑在眼前那些美好，提醒自己更善良，这一生只是永恒暂时的记号。存在的、失去的、不实现都很像，在中间还会再遇到。各种我各自在各宇宙，何别哭我笑，都在这一秒。每次当我沾染黑暗的色调，想象自己有对照，在此刻在某处那个我，他很好。每次当我迷惑在眼前那些美好，提醒自己更善良，这一生只是永恒。